This module aims at explaining in detail special probability distributions. Students, after having gone through this module, you will learn about the Poisson distribution. You would also learn about the exponential distribution. We would also discuss and learn the characteristics specific to each of these distributions and also learn the applications of these special distributions. By now, I am sure you know that probability distributions form an integral part of the probability theory. Probability theory basically involves a discussion on the concept of random variables and their types, events, experiments, etc. Just to recapitulate, a random variable is one whose value is an outcome of a random event. There exist several possible outcomes and the corresponding values that the variable can assume. A discrete random variable may take only certain values which can be easily counted, and they are quite often whole numbers. Random variables of the continuous type, on the other hand, can assume any value within a given range. The outcome of a coin flip or the result of rolling a die are examples of the case when the random variable is discrete. Heights of students in a class, the arrival time of the employees in a company are continuous random variables. A probability distribution is an array of the possible outcomes of an experiment and the corresponding probabilities of each outcome. The probability distribution for rolling a dice or die is shown in table 1 below. In this table, we have the outcomes and we have their corresponding probabilities. I'm sure you know that when we roll a die, the maximum values which we can have, or the possible values which we can have, are from 1 to 6. So in our column of outcome, we have the values from 1, 2, 3, 4, 5, 6, and we have their probabilities. Now, if the die is unbiased, which means each number has the same probability of coming up, then their probabilities will also be equal and are equal to 1 by 6 for each number. And this is what we have shown in our second column of probability, that it is 1 by 6 for each number. The expected value of the probability distribution is obtained by aggregating the product of outcomes with their corresponding probabilities. So expected value is basically defined as sigma xi into pxi. On the other hand, variance is nothing but the weighted average of the squared deviations from the mean, where the probabilities act as a weight. Now, table 2 below illustrates the calculation of mean and variance of a probability distribution. So let us try to explain the mean and variance of a probability distribution of rolling a die. So in our column 1, we have the outcomes, which we can also write down as small xi. We have their probabilities, which we write as probability xi. In the third column, we have their product, which is defined as xi into pxi. In the fourth column, we have xi minus mu square into probability of xi to calculate variance. If you look at the first row, the first outcome is 1. Then we have the corresponding probability 1 by 6, which we also mentioned in our table 1. So first column has the same numbers 1 by 6 again, 1 to 6 again. We have the same probabilities pxi from 1 by 6 for all the numbers in our column 2. And now in column 3, which is a new column in this table 2, you can see we have the product. And these products are 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, and 6 by 6. Now, if you sum them up, what you obtain is 3.5, and this is our mu, which is nothing but expected value of x, is also defined as mean. If you look at the last column, again, we have multiplied 1 minus 3.5 whole square into 1.6. Let me clarify, 3.5 is nothing but the mean value mu, which we have calculated in our third column. So if you look at the column fourth, we have all these products and the simplified value. The first cell in this fourth column gives us 1.042 corresponding to outcome 1, and then we have the values 0.375, 0.042, 0.042, 0.375 and 1.042. And if you take the sum of all these, you get 2.92, which is equal to sigma square and variance. So this chapter basically explains some of these special probability distributions like Poisson and exponential distributions, the assumptions and characteristics specific to each one of them and their applications.
The Poisson distribution. The Poisson, uniform, and binomial are the three most important discrete probability distributions. Poisson distribution was developed by Simon Poisson, who was born in 1781 and lived up to 1840, a French mathematician. This distribution was discovered in the early parts of the 19th century. It measures the probability of a random event within a given interval of time or space, and it is a discrete distribution. It can be safely put that the Poisson distribution arises from a binomial distribution or the exponential density. It is important to look into the assumptions made while applying this distribution. They are: the probability of the occurrence of the event is constant for any two intervals of time or space. The second assumption is that the occurrence of the event in a particular interval does not depend on the occurrence of the event in any other interval. The Poisson distribution can be applied to several real-life instances. The following are a few important examples. It could be applied in the number of deaths resulted due to kicking off the horse in Prussian army, or the number of times a machine breaks down in a month, or spread of any endangered animal in a particular region, or typing errors on a page, and the number of defective electrical connections per mile in the power system of a city. Poisson probability function. The assumptions of the Poisson distribution listed above give way to the following probability function, which is Px is equal to mu raised to the power x into e raised to the power minus mu upon x factorial, where x is the number of times the event occurs, mu is the mean or the average number of occurrences per unit of time or space, e is equal to 2.71828, which is the base of the natural logarithmic system. Properties of the Poisson distribution. Important components of the Poisson probability function have already been stated above. Table 3 below shows important properties of the Poisson distribution. What are these properties? First is mean is equal to mu, variance sigma square is also equal to mu, standard deviation, which is sigma, is equal to under root mu, coefficient of skewness, which is denoted as alpha 3, is equal to 1 upon under root mu, and coefficient of kurtosis, which is alpha 4, is equal to 3 plus 1 upon under root mu. The moment generating function for the Poisson distribution is given as follows. Mxt is equal to e raised to power mu into e raised to power t minus 1. Now this can be shown as follows. Mxt is equal to expected value of e raised to the power tx. Now this is equal to summation e raised to power tx into e raised to power minus mu into mu raised to power x upon x factorial. Summation of x is over 0 to infinity. Now this on simplification is equal to e raised to power minus mu into e raised to power mu into e raised to power t. This is equal to e raised to power mu into e raised to power t minus 1. The moment generating function, once obtained, leads the way to mean and variance as well. Poisson distribution is a special case of binomial distribution. The probability function of a binomial distribution is given as under, which is fx is equal to probability that capital X is equal to x. Now this is equal to ncx into p raised to power x into q raised to power n minus x. This I am sure all of you know is equal to n factorial upon x factorial into n minus x factorial. This into p raised to power x into q raised to power n minus x, where p is the probability that an event will occur in any single Bernoulli trial. It is essentially the probability of success. Similarly, q is equal to 1 minus p and is the probability that the event will not occur. Therefore, it is the probability of a failure. The probability of success for exactly x times in n trials is given the binomial probability distribution function above. The mean for this distribution is equal to np and the variance is given as npq. These can be mathematically proved. In the binomial distribution, if number of trial n is very large, while the probability of occurrence of the event p is close to 0, the event is said to be a rare event. Usually, an event is considered to be rare 1 if n is at least 50 and np is less than 5. In such a case, binomial distribution is closely approximated by the Poisson distribution with the mean equal to np. The mean and variance of any binomial variable should approach those of the Poisson variable. So np and npq both should tend to be equal to mu. The Poisson process. An important application of the Poisson process concerns the occurrence of particular types of events over time. Suppose we begin at a point of time t equal to 0 and the task is to record the number of tremors caused by the volcano in the region. Following assumptions are made regarding the tremors. The first assumption is there exists mu greater than 0, a parameter such that for any short time interval delta t, the probability of recording exactly one tremor is given by mu into delta t plus 0 into delta t. The quantity 0 into delta t is a small fraction smaller than delta t itself. Second, the probability of recording more than one tremor during this short interval is 0 or O into delta t. Now, this together with the previous assumption indicates that the probability of recording exactly 0 tremors is 1 minus mu into delta t minus O into delta t. Third, the number of tremors recorded in the interval delta t is independent of the number of tremors recorded in the intervals prior to this interval. In case of a short interval of time, the probability of recording a single tremor is approximately proportional to the length of time interval, where mu is the constant of proportionality. If pk in bracket small t, which means pkt, is used to denote the probability of recording k tremors during a time interval of t, the expression for pkt is given as follows, which is pk as a function of t is equal to e raised to the power minus mu t into mu t raised to the power k upon k factorial. The number of tremors recording during the interval t is a Poisson random variable with the average rate equal to mu t. This implies that the average number of tremors during the interval of length t is mu t, and the average number of tremors recording during a unit interval is mu. Application of Poisson distribution. Examples. Problem 1. On an average, 2 houses are sold by the Bharati agency per day. Calculate the probability that exactly 3 houses will be sold today. Solution. This is an example of a Poisson experiment in which following information is available, which is that mu is equal to 2 since 2 houses are sold per day on average. X is equal to 3. The probability of exactly 3 houses being sold today is to be calculated. And we know the value of E is equal to 2.71828. Now these values can simply be put into the formula. So we get Px is equal to mu raised to power x into e raised to power minus mu upon x factorial. On substitution of these values, we get 2 raised to power 3 into e raised to power minus 3 upon 3 factorial, and this comes out to be equal to 0.1804. Therefore, the probability that exactly 3 houses will be sold today is equal to 0.1804. Problem 2. Suppose cable in the city power system has 3 defects per 100 yards. If 50 yards are required, what is the probability of 1 defect? Solution. The first step is to express 50 yards as a proportion of 100 yards, which is 50 by 100 and is equal to 0.5. The mean number of defects per 50 yards is computed as 3 into 0.5 is equal to 1.5. So we have the following details. Mu is equal to 1.5, which means on an average there are 1.5 defects per 50 yards. X is equal to 1. The probability of exactly 1 defect is to be calculated. And E is equal to 2.71828 as we already know. So probability of X comes out to be 1.5 raised to the power 1 into e raised to power minus 1.5 upon 1 factorial, and this is equal to 0.3347. So we may say that the probability of 1 defect is equal to 0.3347. Problem 3. Suppose a paving company is hired for the maintenance of roads in a city. It is known that the roads paved by this company on an average have 2 defects per mile after being used for a year. Calculate the probability for 3 defects per mile after 1 year of use. Solution. We have the following information. Mu is equal to 2, which means on an average 2 defects are found per mile of road. X is equal to 3. The probability of exactly 3 defects per mile is to be calculated, and E as usual is 2.71828. So as per the formula, we get 2 raised to power 3 into e raised to power minus 2 upon 3 factorial, which comes out to be equal to 0.1804. The probability of 3 defects per mile of the road after carrying traffic for a year is 0.1804. Students, we have added few more examples which you can read from your e-text. So students, as has been discussed, Poisson distribution is a discrete distribution. The exponential distribution, on the other hand, is a continuous distribution. This distribution estimates the lapse of time between independent events. If the number of occurrences follow a Poisson distribution, the lapse of time between these events is distributed exponentially. An exponential random variable can be explained as the waiting time until the first event in a Poisson process with rate mu. The exponential density function for x is as stated under. X can be denoted as the time lapsed between two successive independent events. We can write fx equal to mu into e raised to power minus mu x if x is between 0 and infinity and is equal to 0 otherwise. The probability function for the exponential distribution is given as follows. Probability x, which is capital X, is greater than or equal to small x, which is a specific value, is equal to 1 minus e raised to power minus mu t. So capital X is a specific value, small x is our variable. Now in this, t is the time lapse and e is the base of natural logarithm system, which you all know is equal to 2.71828, and mu is the mean rate of the occurrence. The mean of this distribution is given by 1 upon mu and the variance is given by 1 upon mu square. The exponential distribution and gamma distribution are related as the former is a special case of the latter. Gamma distribution estimates the waiting time for more than one event. The exponential distribution, on the other hand, estimates the time between independent events. The gamma family of distributions primarily deals with skewed distributional shapes. The exponential distribution is quite closely related to the Poisson process as discussed at the beginning of this section. Suppose that the number of events occurring during any time interval of length t has a Poisson distribution with parameter mu t, and that number of occurrences across different time intervals are independent of each other. The distribution of time lapsing between the occurrences of two successive independent events is exponential with the average rate of mu. This can be verified by a quick exercise. Let us look at the case where t1 is the time until the occurrence of the first. Then we may write probability P of t1 less than or equal to t is equal to 1 minus probability t1 greater than t, which is equal to 1 minus probability that exactly 0 events occur in the interval between 0 and t, and is equal to 1 minus e raised to power minus mu t into mu t raised to power 0 upon 0 factorial. Now this is equal to 1 minus e raised to power minus mu t. So the Poisson distribution can be used to arrive at the probability function for the exponential distribution. Applications. The exponential distribution estimates the time lapse between two independent events in a Poisson process. This distribution has a diverse application and can offer solutions to real-life problems. Exponential distribution can model a variety of events. Following are a few examples. the time until a radioactivity particle decays, the time it takes for a consumer representative to cater to a customer, or it can be the number of miles that a vehicle can run before its battery dies out, or the probability of the arrival of a phone call within the next hour, or the time between machine breakdowns, or time is taken for the next assignment to be given at a call center. Shape of the exponential distribution. The distribution of a random variable following exponential distribution is shown in figure 1 above. The curve declines continuously, implying that as x rises, the probability attached with it falls. Students, we have in our e-text added some examples for exponential distribution for your clarification. I would recommend that you go through all these examples from your e-text. But let me take just few examples here. Problem 1. In a restaurant, customers arrive at a rate of 8 per hour. Calculate the probability that more than 50 minutes pass between the arrival of two customers. Solution. The mean rate of arrival of customers is 8 per 60 minutes. The proportion of 50 minutes to 60 minutes is 15 by 60, which is 0.25. So t is equal to 0.25. And mu t will be, or minus mu t will be minus 2, as the value of mu is 8. So 8 multiplied by 0.25 gives us 2. To calculate the probability that the arrival time will exceed 15 minutes, we need to estimate the probability for the case when the time taken for interval is less than or equal to 15 minutes. That means probability of x less than or equal to 15. And this further can be subtracted from 1. The values can be substituted in the formula for exponential distribution. And what we obtain is that probability x is less than or equal to 15 is equal to 1 minus e raised to power minus 2. Now this is equal to 1 minus 0.1353 and is equal to 0.8647. So the probability of x less than or equal to 15 is 0.8647, and hence probability of x greater than 15 is equal to 1 minus 0.8647 and is equal to 0.1353. Therefore, we can say that the probability that more than 15 minutes pass between the arrivals of two customers is 0.1353. Let me take one more example. Let's understand. Suppose the mean rate of arrival of trains at a station is 1.5 per hour. Calculate the probability that not more than 2 hours will lapse between the arrivals. How do we solve this? Look at the solution. In this problem, mu is 1.5 and t is 2. So minus mu t is equal to minus 1.5 into 2 and is equal to minus 3. In table A, as the row with x is equal to 0 and lambda is equal to 3 needs to be looked at, the negative sign attached with mu t needs to be ignored at the moment. The table gives the value of e raised to power minus 3 equal to 0.050. Therefore, probability that x is less than or equal to 2 is equal to 1 minus e raised to power minus 3. Now this comes out to be 1 minus 0.050 and hence is equal to 0.95. Therefore, the probability that not more than 2 hours will lapse between arrivals is equal to 0.95.
Let us students try to summarize the entire discussion in here. We have learned that the probability distributions form an integral part of the probability theory. We have also learned in this chapter that how we can have special probability distributions like Poisson and exponential distributions. We have seen that the Poisson probability distribution basically measures the probability of a random event within a given interval of time or space, and it is a discrete distribution. We have also learned that the Poisson distribution is a limiting case of binomial distribution. On the other hand, the exponential distribution measures the lapse of time between the independent events in the Poisson process. We have seen that the exponential distribution and gamma distribution are related, as the former, which means the exponential distribution, is a special case of the gamma distribution, which is the latter distribution.